Okay, so yeah, stream died before. No idea what happened. Sucks. Uh, I guess I hope you watched it before. Don't know. I guess I'll just continue on from here. Oh yeah, where was I? Because I got all mixed up. Okay, so this represents 0, this represents 1, this represents 2. Now, how would we check if either of these are on? Because, well, of course, 0, 1, 0, 1. Let's let's try 1 plus, this is an adder by the way, 1 plus 0. Well, we'd expect a 1, obviously. But we also want to check that this isn't activated at the same time. Because think of it. If we want if we want it to equal 1, then that means one of the buttons has to be on and the other has to be off. So what we use for that is an XOR gate, or exclusive OR. So what that means is we check if either of them are on, and if both of them are on, we turn it off. Well, yeah. Oh yeah. Oh, the stream got cut before, so I didn't explain what an OR gate was, didn't I? Oops. Okay. Well, anyway, it's modified OR gate. An OR gate is honestly the easiest one out there. It just checks if either of them are on, and just outputs a positive signal if either of them are on. That's it. So what I used here is a NOR gate, which is kind of the opposite. It combines a NOT gate and an OR gate. NOT meaning, well, if I put a 0 input right here, then I'd get a 1. If I put a 1 as an input, I'd get a 0. So it just gives the opposite. So the opposite of an OR gate is that it's on when both of them are off, but off any other time. XOR gate, off when both of them are on. So 0 plus 0, well, that's 0. 0 plus 1, that's 1. 1 plus 0, it's 1 again, obviously. And 1 plus 1, 2. Scrap Mechanic lets you use this little wiring tool. So I feed wires into each of the logic gates so that they can each receive both of the both of the inputs. And then they output to the lights, their own respective lights. That's a 1-bit adder. It's really simple. Now, with 2-bit adders, it gets a little bit harder. So, of course, you start off with the same system as you used before. 0 plus 0, because, yeah, let's just assume there's only one digit on the right like before. 0 plus 0, 1 plus 0. Yeah, it's pretty simple. So let's do this a different way now. But, well, actually no. Let's do it the same way. Because we'll just do the same thing for the left side. So for this left side, we'll just add the 2 up like we did before. And then we get another input, well, another output for the second place. Remember, do you know binary? This, the digit on the rightmost starts as with 1, and then the more left you go, it doubles after every time. So let's try to write the number 5. You add 1 and 4, because 1, 2, 4, 8. This is 4 bits. You can represent any number from 0 to 8. This is 0, This is 8. Well, no, sorry, not 8, but actually 15. This is 0. This is 8. This is 12. This is 14. This is 15. The highest you can go. And of course, if you add one more to that, it all overflows and goes back to 0. So, let's try to represent 5. 4 plus 1, done. 7. Well, that's 4 plus 2 plus 1. 4 plus 3, 7. 9, 8, 1. It's a simple system, and it's the basis of how computers work. So let's try to add 3 and 2. We'd expect an output of 5. So how would we get that? So add the first two. Let's just think of regular math. You have the two numbers right here. Say, think of base 10, where you have like the first digit right here, the second digit right here, third digit, 122, 276. First you add the right line, then you add the middle, using the, well, this you get 13, so you put the 3 down here, and bring the 1. Then you get, what again? 1 plus 2 plus 7. It's 10, so you put a 0 down here, bring over the 1. 1 plus 1 plus 2, that's 4. So we get 403, I think. I don't remember if I got the right numbers, but yeah, we're just going to use the same system right here. So we have 0, 0, 0, 0, well, 0, 0. If we have 1 plus 0, well, that's just 1. But if we have 1 plus 1, well, that's 2. We can't represent a 2 right here, so we carry it over into the 2 column. 2. And then whatever we have here, we'll just do the same thing. That's a big number, so that would result in 2, 4, 6, well, and the next column is 4. So it would just overflow to 4. So what our number looks like now is that, let's see, so 3 plus 3 equals 6, which is 4 plus 2. I hope I got this right. I hope I got it right. I mean, I probably didn't, but I hope I got it right. Let's see. So, now how would we do this with logic gates? Well, do the same system for each of the ones, obviously. But you have to have a third input. Now, how the heck would you get a third input? How do you get a third input in there? Well, you just add the first two, and add the next one. That's it. So, to do 3 plus 2, we'd first do, let's just draw it out right here, 3 plus 2. We'd first check, okay, there's only 1 in this column, it doesn't overflow, that's 1. This column does overflow, so that ends up being 4. And so we see what's on this column. That ends up being 4. And well, 3 plus 2 equals 5. Let's see if that's right. 4 plus 1, 5. I haven't explained how to do it though, that's the problem. But I've already built this actually. So what it does right here, it checks So right here in these 3 logic gates, I'm just copying, well, these 6 logic gates actually. 1, 2, 3, 4, 5, 6. I'm just copying this twice. AND, NOR, XOR, NOR, XOR, AND. I just put it in an order which actually makes sense this time. NOR, XOR, AND. So yeah, so I get the input, so I get the output. Oh yeah, I reversed this by the way. So this represents 0, this represents 1, this represents 2. 0, 1, 2. 0 plus 0 equals 0. 1 plus 0 equals 1. 1 plus 1 equals 2. This is regular base 10 and stuff. Let's try it again. 1 plus well, this is actually different this time. This represents 2. 2 plus 0 equals 2. 2 plus 2 is 4. And 0 plus 0 is 0. Wow, these are annoying. Okay. So now we have the results right here. So let's say we have this. Now we have the results of these, which I'm just going to use 2 digits for now, which is exactly, wait, 3 plus 2 is 5, so that's 1 and 3, 4. 1 and 4. So now we need to, well, no, 1 and 2 twos actually. Because, remember, we had both of these adding up to 2. What am I doing right now? What am I doing right now? What am I doing? No. This added up to 1. So we had nothing here, so it's just 1. Then both of these added up, so there you go. Now it's overflowing. And well, what do we do now? Well, we just continue with it. Add both of these together and get the third one. Easy. So get the normal calculators going. We get the, this is really bad explanation, sorry, but we end up with 2 plus 3. Okay, here we go. Let's see. And I use this to represent it easier. This represents 1, this represents 2, this represents 2, this represents 4. So right here, oh my god, what did I do with these again? Okay, so if I get a 1 for both of these, if I get a 1, well then there's no other reason why the rightmost one would be on. So I just activate this piston to represent that the 1 is in place and stuff. Then, yeah. 2, I'll check if this one is on. And if it is, well actually no. If both of if I get the 2 from both of these, I'll put it here. I didn't get it from here. I only got 1, so I'm putting it right there. And then this is for the second part. See how this is blue and this is red? The second part, the left part goes to the blue, the right part goes to the red. See how it is? Anyway. If one of them is on, it goes to 2. If both of them are on, it goes to 4. Do you see something right here? We have 4 different pistons right here. Remember the columns when you're adding? Of course, this isn't here because, well, it wouldn't need to be here. If it's 0, well, it's 0. None of them are on. And we just give a 0. Pretty simple. I haven't actually explained how this works though, so I'm going to explain. I give all the inputs, give all the inputs, then, well, I actually don't use the zeros because, well, why would I? I'm not saying if the output is 0. Right here I'm giving the output in binary. 4, 2, 1. 4 plus 1 equals 5. Then I output it to here using this system, and then I add these two by checking if this piston is up, and it's only up if the logic gate is on. So I'll check if both of them are up, and if they are, then I'm gonna activate the one on the absolute left, because that would mean 2 plus 2, and of course that's obviously 4. And then I'd have to deactivate these ones because, well, I don't want it to being 4 plus 2 plus 2 plus 1. It's not 5. And 3-bit adders are the exact same thing. I'm just carrying it over another time. Yeah, they each do their calculations individually. Same system. Yeah. I hope you understood. I really hope. Because it's about to get a little more complicated. So, right here I tried to build a 3-bit memory registry. What the heck does that even mean? Anyway, I might have even just made that up. I don't even know. 3 bits? Well, you can represent a number from 0 to 15. Remember that. So that's up to 15 memory locations. Well, actually 16. It's 16 memory locations because, of course, counting with computers always starts at 0. So 0, that counts as the first one. And then all the way up to 15. And the 15th is actually the 16th. So instead of starting at 1, we start at 0. I hope that made sense. Let's see. So what I was planning to do with my system is I give the memory location up here, and then I give the actual number to my computer right on the bottom. So let's say I want memory location 3 to be set to 4. Oh no. Oh yeah, 3 bits only adds up to 8, by the way. I made a mistake there. So 3 plus 4, I mean 3, the memory location 3 is going to be set to 4. So 1, 2, 3, this would be set to 4, which is this. I didn't actually get around to making that work. What I did, however, get around to is building like a normal digit array. So 1, 2, 3, 4, 5, 6, 7, 8. When I push this button, it lights up the correct one. 3. This light lit up. 1, 2, 3. So how this works is basically there's tons of wires which make absolutely no sense. And ignoring that, what I'm doing is checking for each number if it's 1, basically if both of these are off and only this one is on, then I output a positive signal and all the other ones are negative. So only this one turns on. And same thing for 2. want to check if this one is on, so I check if these two are off, and then I output to right here if they are off. And it took me a while to realize what to do for the system of checking, but actually the system wasn't even that hard. So I took XOR and an OR. XOR and OR. Doesn't that feel a little similar to XOR and but NOR? It's weird how that works. Weird. So, what would this do? Let's give it the 3 inputs. So we want to check if it's 1. I should probably check. I should probably try to remember how this worked. Okay. So I want to check if it's 1. So 1 has to be on and all the others off. So let's just use an XOR gate, right? So if this one is on and either of these, well, let's just use an XOR gate and an OR gate, right? So let's put them both into here, and then put this one into here, and oh look, so we're checking if either of them are on, we put it into here. So if either of these are on, and this is on, then we turn it off, because we don't want it to be detected as 1 if any of these are on, so why would, so that's exactly why. And I do keep that part of the system right here. But there's a catch, because, of course, like, if both of them are on, you still want it to activate. Well, let's say only one of them are on. I mean, or just like in a special case where, let's say both of these are on. Say both of them are on. Both of them are on, so it outputs a positive, well, or XOR. So we want it. So that would mean both of them are on. It activates the OR gates, but oh look, it activates the XOR because, well, that one isn't on. We could be trying to do a different value. So how would we fix it in the end? I don't know why I just removed those buttons. We check if this one is off. So, OR gate. We feed both of these into OR, just to get our 2 bad signals. We see if either of them are on, and then we stop the signal if this is on too. But we also want to stop the signal if this is off, because of course there's that situation. So I put this into the AND gate along with the output of our previous XOR, and we get magic numbers where we just get magic. The output is positive if it's 1, and negative if it's anything else. Well, you saw it flash right there, but that's just because I can't stop the delay in Scrap Mechanic. So basically this is just that same process repeated each time for each of these. And of course, for when I want 2 numbers on, I just check if both of them are on using an OR and just hooking it up in a different way. So how would this work? Well, this is a little bit simpler. I built a 2-bit system instead. And, well, it actually doesn't work 100% good, but, you know, this stream was supposed to be mainly about trying to fix it, but I just realized that, wait, no one would care if no one knew what was going on, of course. So At least I got that explanation out of the way. We can start moving into this mess that is all these logic gates. So each of these cells are memory cells. It uses a SR NOR latch. If you've played Minecraft and have tried to make a SR NOR latch before, you'll know that it just takes two redstone torches, which are essentially just two NOT gates strapped together. So you got the set. I could bring up a photo on stream. It's true. It's true. I don't know how to do that though. Anyway, if you wanna, so let's say this is our output right here. So if this is on, which, well, if it's on, it's blue. If this is on, then it's 1 or true or whatever you wanna think about it in binary. And of course, if it's off, it's off. Yeah, simple. So how would we flip the memory cell? Well, we just feed something into the other output. It doesn't make sense, right? But think of it. If think of the system right now. If this turns on, this NOR gate will then. Oh, sorry, no, it goes the other way because. Oh yeah, Oh yeah, okay. Sorry. If Okay, so if this OR gate turns off, then that's going to activate this NOR gate. That's then going to activate this OR gate, because they feed into each other in an anti-clockwise pattern. And since this is off, this is on. And since this is on, this leads to this, which is positive or on. And it just stays like that. Perfect. We've got it stuck in some sort of like in this sort of position. And to get it unstuck, we just, well, strap an input to the other side and boom. Because this is an OR gate, it can accept 2 or 1 input because, well, this is also scrap mechanic and that's just how stuff works. Since I activated this one right there, that then deactivated that NOR gate, that deactivated this OR gate, which kept this NOR gate on, and, well, you see the cycle again? It's here. So if I set this one again, then that inverses the signal, and we kind of get like a place where this is the one that's off. If you turn it on, then it kind of like resets it to the other side. So I just use that a lot of times, and, well, right here I'm using, well, similar to what I wanted to do over there. I give it a memory location. I set it what it wants, what I want to set it to. This is memory location 0. This is memory location 1, 2, 3. Oh yeah, and remember, there's two memory cells because I have to store 2 bits. So, memory location 0, which is that one, I want to set to 0, so I'm turning both of these off. And what I represented as off in this situation is that the bottom OR gate is on. So 0, 0, 0, 0, 0, 0, 0. But remember I set this to 1, so I want to reset it. Reset. Oh, that glitched the system. Okay, it's all good now. So what I do to reset it, I just check if this is, I just check the memory location to see if it's 0, and I check if this is on because, well, I don't want it constantly giving an output and me putting in an instruction that I don't want to really mess up with other stuff. And I don't want to always reset it, like, come on. So, I check if... Yeah, this is the new way I organize the system. So I check if it's in the 0 position, which is this one, see? And that the button is pushed. And then I reset it, which is the bottom one, of course, like I said before. And then I just do the same thing for any of the other memory locations, check if it's that specific one, set it to whatever's entered here. Not that much. So what the heck is all that for? This purple zone is represents like how we find out what memory location it is. Zeros. See how the switches are purple too? Purple for memory, orange for the actual value you're giving it, and yellow for giving it a certain instruction. Right here, I'm just giving it the set instruction, but if I turn this on, well, since I only have 2 instructions, I only have to have 2 states, so I just put a switch there. So I just check if this is on, and if it is on, well, I add the value to the memory location. It's a difficult system to wrap your head around because there's a lot of connections. I'll try to, yeah. So, purple finds out which memory location it is. Orange finds out the value. Wait. Wait. Wait, does it? Oh yeah, it does. Well, oh yeah, pink is for later, I think. Pink is, actually, what does this do? What does this do? Oh yeah, pink. So, that just, of course, deals with the, well, of course, what do I mean? What do I mean? That's not obvious. It just assigns the value to the memory by checking if, let's say, I wanted to set it to memory location 0. So I check if 0 is on, using these 2 logic gates. And I check if either of those are on. If that's on, well, the right one goes on. If both are on, both of those go on. And then I just put it up to a timer because scrap mechanic's glitchy. And the SR NOR latches don't always work. Which is why if you do this, everything goes mad. So let's think of the process. Reset, set again. Well, find the memory location, reset that location, set it to the new value, done. Same thing for all the other ones. There's a lot of repeating going on. Let's try adding. So I find the memory location, I check what value it is, and then I add a new value to it. If it's, well, if it's 3 plus 3, or, well, honestly, 3 plus anything, I can't go over that, so I just overflow, and it doesn't work at all, because I never got around to fixing that problem. So let's see. I want to add memory location 0. I'll set to 1. There you go. Now I'll add 1 to memory location 0. So what that should do is set it like this. But because my system is glitchy and doesn't reset properly, this stays on. And I haven't figured out a way to do it because I'm a little unorganized here. what I did find out what I had to do was, well, I did the same thing I did here. I find what values I need to put into the calculator. So 0, 1, check if the check what memory location I'm putting it into. So same thing here. Check if those two goes on. Well, because, oh wow. Oh, that's the difficulty. Okay, so yeah, this is all flickering because all that's flickering. Okay. Anyway, this should be the only one on because this switch is the one on. And then if it's a different memory location like 1, it's down here, 2, down here, 3, down here. Then it kind of goes weird again. Because, well, why am I separating it into different channels? Wait, yeah, why? Yeah, wait, why am I setting it to different channels? That's true. I never thought about that. Why am I setting it to different channels if I'm just putting them all into the same ones and then just putting it all into the same calculator? Because instead of making 4 calculators for each potential value, I mean, come on, that makes no sense. I just fed all values into that. And then what I decided to do was then check the memory to see which one I should set it to. You know, that actually might be where my problems are at. Let's see. Oh yeah, because in Scrap Mechanic you can set an infinite amount of things. Infinite amount of inputs on an OR gate or NOR. And it will still work. But only those two. Because AND, well, come on. That doesn't always make sense. And XOR, well, what do you do if there's 3? What? That makes no sense. So yeah, I guess I'll just remove this real quick. So... Actually, yeah, okay, let's see. This links up directly to... this should link up directly to... Oh, yeah! Oh, that... Okay, this... I thought this system was for the bottom values. I was mistaken. I was right in sending it immediately over there. Like, that's obvious. So I just add whatever values there to the memory location. Because, well, I'm adding those two together. So this gets the value from the memory location. That's why this was flickering. Because this was flickering. So these are both 0. Let's just try a different location. So, yeah. This system was 0, so these were both 0. Simple as that. And I wasn't adding into anything to it, so it wasn't changing. I get the calculator going. Thing from the value from the memory, and then the input. So let's say 1 plus 2, 3 obviously. This is 3x in binary. 4, 2, 1, 2 plus 1 equals 3. And then I find out what memory location I should set it to again. Does look familiar to the pink because it does the exact same function. And then I set it. What I'm probably doing wrong here is that I'm not resetting it, but that's what this system is for. That resets... That should reset them. Huh. Because this seems to only reset the first... Oh yeah, because this only resets the first location. Because, well... If I'm gonna set a new value to only the first one, I don't want it erasing everything I have so far. Ugh. I'll just reset that real quick. Reset. Reset. Oh, I'm still in adding mode, so it's still glitched. Right, perfect. So, no idea what's going on with my system. But what I could do is maybe build a more stable memory loop, because there's such thing as an SR and latch, NAND latch, I think. And I'll test it out with my convenient system over here that is still overly complicated, so I'll just make a new 2-bit one. Actually, no. I'll just make a 1-bit one, because I'm just that lazy. So, I'm getting this from a YouTube video. I don't remember exactly. I'm not an expert. Leave that up to the experts. So, get an OR, and knots, but since there's no knots, get an OR. Oh yeah, right, we need 2 inputs. Set, reset. Set, reset. Set, reset. So, reset gets fed into the NOR. This gets fed into the AND. The set gets set into the OR, into the AND. If this is set, then it's on. If this is... Oh yeah, right, it doesn't work yet. So, I'll set up a light. This is the output of this. But also add another thing. I make this link directly to this one. So, since Scrap Mechanic doesn't let you do that, I'll just make an OR gate. So, if this one or this one is on, meaning if this one's on, then I output this. It's a little nice workaround. Set. Set? Wait, set? Hello? Oh, this is an... Oh, this is an N, not an OR. Okay. So, set. I set it on. No, look, it stays on. But if I reset it, there you go. So what's going on here? This is what's going on here. It gets stuck in a loop again. So if I let's say it's on. Let's say I've reset it. It turns off. Actually, no. I should probably start off with set because that makes more sense. Set. I'm gonna set it to on. So what I'm doing, I'm turning the OR on, and that means this one and the OR is on. So I output a positive signal. But wait, since I'm outputting a positive signal, I'm also outputting a positive signal to here. And it's looping back to here. So if I turn this off, well, I don't really need it anymore. The output of this replaced the input. It goes in a loop. And then this stops the loop because, well, this turns off the output. Well, this turns off the end, then that turns off the input feeding itself. Done. Maybe I'll get this done for another time, because I don't have time. No, it was a weird experience doing it alone. This wasn't particularly exciting because I'm by myself, and the stream glitched in the beginning, and everyone left because that's boring. So, that's it. Maybe I'll explain another time. Maybe I'll build something else. It'll be fun. Bye bye. Bye bye to no